Assalamualaikum warahmatullahi wabarakatuh. Selamat Hari Raya. I really miss everyone. So here is some tips. Overview of chapter number 6, which consists of chapter 17 and 18 in our book of survey lah. So in this particular topics, there are basically 6 things or concepts to understand. Started with the idea of current, and then how current bind together with the idea of Ohm's law, V equivalent to IR, and how in the Ohm's law there's this factor called resistance, and how these resistance are affected by build-ups, how it was build-ups, and also the surrounding, which is the temperature, and then the consuming of the energy in the form of what number 4 we call it energy and power, and then how we can arrange the resistor in two ways, resistor in series and parallel, and finally a methods on solving, we call it as Kirchhoff law. Number 1, so when we start talking about current, we have to go back a little bit on previous topic when we learn about electric charges. So if you can recall the idea of electric charges, the electric charges are due to movement or transferations of electrons, and in this case you can see that a balloon gather up electrons, and electrons are considered as charges, and in this picture shows that it gets stuck to the cats. Okay. However, when we start talking about the current, the difference is that now those charges that supposed to be static are now in motion. So electron is a flow of electrons. Electricity is a flow of electrons. So that's the reason why when we define current, it's actually number of charges over time, or in this case it says that rate of charge. Rate represent division with time, and charge divide by time. Unit here is ampere. If let's say the value bears 1 ampere, then it means that 1 coulomb per 1 second. 5 ampere, 5 coulombs per second. Right, so you can see here the battery supplying energy to the electron and allowing the electron to pass through the metal wire and later on light up these particular bulbs. Right. Now, so there are 3 things that bind together by using the concept of Ohm's law. Okay. So Ohm's law is V equivalent to IR. Originally in the book it used to state as V over I, for the reason, okay, V over I, because the R in most material is supposedly to stay constant, okay, and therefore when you apply bigger voltage, hence you're going to get consequence of bigger current, and units of resistance is considered as ohm. Okay. So ohm is also equivalent to volts over ampere. So based on the expression, right? Now, so you find that right. So you find that resistance, the idea of the resistance is similar to the name itself, to the words itself, to resist. So likewise in this figure, this red ball is actually electron able to climb up because supply with the energy, and then as it pass through these resistors, it start to slow down. So resistant, oh right, so we have to go back. Resistor is the device. Resistor is the device. Resistance is the amounts of the resistance, amounts of the strength. So it arises because of the collision between electrons and the atom inside the conductor. So it slows down the motion of the electrons. For the use, we find that we have the common voltage coming from TNB. However, our device like your handphone, televisions, microwave, your laptops, this device require different amounts of current, and that's where the resistance comes in to reduce to the correct amounts of current required. Right, a little bit to ponder and recall the idea of Ohm's law. If you remember from high school, ohmic and non-ohmic material, I need you to come up with this. Differentiate between ohmic and non-ohmic material. Use this figure to help you out. So one is like a straight line, linearly, and the other is a bit curvy. Right. So I did mention that resistance are affected by four things. Which number 3 of them is this. This is rho, okay, which is considered as resistivity, L length, and finally area is cross-sectional area. This is this cross-sectional area. So it means that these three elements are the physical build-ups of the metal. Now we can understand that length of the wire, right? But how does a length of the wire affect the resistance? Now let's assume that every one of us are now on highway. Okay. Now we have 3 lanes, we have 2 lanes. Alright. So and also you're moving like from here, Pahang, to perhaps Perak, okay, and another consideration is from Pahang to perhaps just Selangor. So Selangor is much shorter. So basically if we assume you as an electron, you definitely will get to the Selangor in much shorter times than going to Perak. So that's how length affect the resistance. Okay. In terms of the area, the analogy that I like to use is, let's assume the highway just now are making use of 2 lanes and 3 lanes. So notice that if the 3 lanes, which area gets larger, then the traffic will get smoother as well. So that's why resistance is inversely proportional with the area. The last one, resistivity. So resistivity, here I'm saying that if you have your textbook, you can refer to this table. What's important is not for you to memorize the data, but for you to understand that resistivity of different metal is different. So in short, resistance is proportional to the types of the material. So resistivity shows the types of the material. They are just different. Right. Next. Alright, this is the fourth conditions or the fourth factors that affect the value of R. So just now go back. It was the metal, the types of the metal, which resistivity, length, finally the area, and now we have a new one, which is the temperature. Oh, okay. So look something at both expression. So this is linear expansion, the one that you learned in physics, earlier physics 2, and while this one is today. Okay, notice that they are quite similar to one another, resemblance. So I hope you can memorize by using this version. Alright, so how so? You will find that the value of this resistivity of metal, somehow they change with temperature. The table given in the book just now is actually at 20 degrees Celsius. At 20 degrees Celsius. So if it gets larger or it gets smaller than that, then you need to recalculate once again. Okay, but don't worry much about this expression because we have another version. Right. Now moving on to the next one. Okay, so let's look how exactly temperature affect the R. So as we are aware, if we are hot, then we will not be sitting still. It means that we are vibrating much more. Okay, so it goes the same with the atoms. They just vibrates more. They cannot sit still. So what happens is the electron need to pass through in between the atoms. So when this happen, as you can see, in terms of the hot wire, everyone is busily moving, including the electron. So it just simply make harder for the electron to pass through, right, as compared with this cold wire. So the electron travel much faster in this cold wire. Right. So how do we go to the equation that we need? So I did mention just now this expression. Don't bother much. It's there, but most of the time we don't use it. So what we did is we do combination of this expression, the one physical variation to get to the resistance value. So this expression on the left side, and also on the right side, we times with length over area and length over area. So you notice that this product now is also equivalent to this product, and that's the reason why it's being replaced with resistance equivalent to initial resistance. While this one, okay, this is a coefficient called temperature coefficient, temperature resistivity actually. Yeah, so this is the expression that you need to remember rather than this expression. Right. Now, let's now move to the fourth things, the idea of the energy and power. Okay, electrical energy and power. So, here, this figure trying to shows you that the energy is being supplied by the battery, generator, or and here you notice that, oh, every time the energy is applied to this electron, okay, they are able to climb up, meaning that they receive potential energy and allowing them to continuously moving, or else they just simply stop here, right? And then when they meet up with a resistor, the resistor simply slow down, like you're trying to move through stairs. Okay, so you need to slow down, you don't just jump down, right? Okay, right. So that's the idea of the resistor, and also the idea of the energy supplied by the battery. Okay, anyway, so as it pass through, what most important here is as it pass through a resistor, it definitely will lose its energy. Why? Because there is a collision with atom in the resistor. Okay, this is something that you learn in physics high school. Okay, number one, power is also knowledge or equivalent to energy over time, and this energy is equivalent to QV. QV. Okay, if you recall, this is coming from chapter potential. Chapter potential. So when you divide with times, you notice that again, this expression is now is QT. Q over T is definition of current. So that's the reason why power is also defined as the product of current times the voltage. Current times the voltage. And when you alternatively gets Ohm's law into this expression, it could either be I squared R or V squared over R. Okay. Nevertheless, don't worry. You can just go back to this expression and at any time just sub Ohm's law. Ohm's law, which is V equivalent to IR. So if here is now replaced with VIR, so you find that it's become V ohms. So this is IR. So just replace one symbols here. So I times R. So that's how you arrive at I squared R. Right, it goes the same with V squared over R. You replace the value of I with the Ohm's law. Right, another famous version is this idea of kilowatt hour. Okay, kilowatt hour. Right, so let's see. So something to recall that power is also watts, right? Now, how does kilowatt hour measured? All right. So number one, kilowatt hour is actually equivalent to 3.6 to the power of 6 joule. Okay, of 6 joule. Now, rather than writing as 3.6 to the power of 6 joule, wow, take long time to spell it out. Okay. So they tend to write it as 1 kilowatt hour. For the reason, this is much easier to digest. Look at K bear the value of 1000. 1 hour bear the amount of time 3600 seconds. So we do the maths together. You find that you arrive at 3.6 to the power of 6 joule. So in short, 1 kilowatt hour is also equivalent to this number. So easy to remember, eh? Okay. Right, so a little bit of this idea. You're going to see these terms in the book. We call it as EMF, electromotive force. So electromotive force is any source, anything that give off energy that can maintain current, okay, in a closed circuit. Example here is battery and also generator. So since battery associate is volts, I think you can recall lah. Alright. Now, how does resistor is considered to be in series? Alright. It's considered to be in series when there is just a single wire from that resistor to the other resistor. So between R1 and R2, there's just one single path here. So when that happens, the value of the resistance can simply add up. Likewise, R1 plus R2. Okay. However, their voltage are different. This voltage and this voltage are different. Okay, so 2, 4, 5, 7. 2 plus 4 is 6. 6 plus 5 is 11. 11 plus 7 is 18. So you get a single equivalent resistance. Now, when you see the second one, which is parallel, it's considered as parallel because there was this junction, and this is just a single lane from this battery, but later on it meets a junction, so it needs to break up. Okay, so current in Malay is arus, and arus you can associate like water lah. When you say water, you can imagine there is a path. Okay, I have a cat here. Right. So the current, when it gets to, well, a channel that is divided, water, when it gets to the, so it simply gets divided. So that's how you differentiate whether it's series or parallel. Do you see any junction or not? Okay. Okay, junction. Okay, here goes. Alright, however, their voltage would be the same for the resistor from here to here. So from here to here. So from here to here. Okay. If we go back to the series just now, the voltage would be different. Okay. However, their resistance is much lower. Why? Because when you do the summation, you need to use this expression. Okay. 1 over R plus 1 over R. And if you recall, capacitance, if they are arranged in this manner, their value of capacitance would be added up. So capacitance and resistors expression are quite opposite to one another. Right. Likewise, 1 over 3. Okay, notice that the current, it meets up a junction and then get divided into 3. So in simple case, we find that, oh, this current is also equivalent to this current plus this current plus this current, I1 plus I2 plus I3. So total resistance should be 1 over 3 plus 1 over 6 plus 1 over 9. And final product, inverse them. Right. This is the last one, the last idea. We call it as Kirchhoff. This is a technique used when you cannot reduce the resistor to one equivalent resistor, or probably there is a battery in more than one battery. Okay, there are two rules. Okay, number one, we call it junction rule, loop rule. The use of this rule is to create the mathematical expression. Use of this rule is to create mathematical and also mathematical expression. Okay, right. So junction rule, loop rule. Okay, let's look at junction rule. So junction is where you have to figure out at the junction what happens to the current. So in this case, the current get divided into I2 and I3. So mathematically, I1 is equivalent to I2 plus I3. Right. Likewise, this example. Okay, go to the book. Look at example 18.4. Okay, 18.4. Okay, I am choosing junction C here. So I'm cutting it out, and you find that there was this I2 moving upwards, I3 moving downwards, and originally traveled from here until here is I1. So in short, I1 is equivalent to I2 plus I3. So you have the first expression. Now there was these three expression required. Why? Because we have I1, I2, I3, three unknowns. So definitely you need three expression. Okay, three simultaneous expression. Right. So the second one is loop rule. Junction rule, loop rule. Okay. This is loop rule. What is loop rule? We look at the circuit, we identify closed circuit. So this is the first loop. Look at how I take it out and shows you that it is a closed one. Okay, so this closed one consists of 5 ohm and 9 ohm, and the current travel through it is I2, which I2 would travel from here up until D from the top, while I3 will travel from the bottom. Okay, and the idea of the loops rule is summation of voltage. Oops, it's not there yet. All right. So this is the second loops. Okay. So second loop is the bottom loops. The bottom loop. So again, it's closed. So the first one is from here to here, and the second one is from here to here. So this is how we arrive at this figure. Now these blue loops, okay, you can draw using your own creativity, either going clockwise or anti-clockwise. No problem at all. You definitely will arrive with the correct answers as your friends, right? Now, how do we get the expression? Okay, this is the first loop just now. Okay, so I did mention that I2 would travel through 5 ohms and then end here. I3 9 ohms. Okay, so the total voltage is equivalent to 0, means, and it's already an expression. So it's already an expression. Your job is to determine what is element of voltages inside this loop. So in this case, we find that 5 times I2 means voltage through 5 ohms, voltage through 5 ohm plus voltage plus 9 ohm. And here, since it's equivalent to 0, it's definitely lah, by logic, one of them would be a negative product. And how so? How so? This is the technique. Okay, if the blue, loops and also the current travel in the same direction, then they will be negative. This is the case. So have a look that the current just now and the blue loops, I2 and also the blue loops in the same direction. That's the reason why it's negative. Means if the other way around, like this, okay, like this, opposite direction, positive. Okay, easy to remember. So recall balik. Junction rule. Now loops rule. Loops rule, where loops you can draw at your own version, clockwise or anti-clockwise. Okay. And if they are the loops and also the current travel in the same direction, it bear negative voltage. Negative voltage. Right. This is the third expression. The third expression. Okay. We look at the second loop. Okay. So based on the second loops, again notice how negative 4i2. Negative 4i2. Let's just double check. Okay. 4i1. This is the current to the right. Okay, current is to the right. The loops is to the left. No, to the same direction. Sorry, the same direction. So that's the reason why it's negative. Okay, right. So the new one, the new technique is voltage. Okay, how do we know the voltage would be negative? Sorry, the voltage or EMF or the battery. Okay, how do we know we are going to put it positive or negative? In this case, it's positive because this blue arrow is pointing to the positive plates. Positive plates is here on the left side. Arrow is moving also to the left. So they are synchronized. Therefore, it's positive. However, if you're using Ohm's law, IR, then you need to find that the current and also the loops must travel in the opposite direction, then only they are positive. A bit confusing there, so get it right. Okay, now once you are here, you will get these three expression. 1, 2, 3. 3 marks already. Okay, 3 marks already. Right, now this expression, in order to solve, you can just simply use your calculator. Press mode, equation, and choose your unknown as 3. Maknanya 3 benda tak tahu. I1, I2, I3. Okay. Now, you will see that there was this A, B, C, D in the calculator. And also 1, 2, 3. 1, 2, 3 represent your expression. Expression 1, 1, 2, and 3. A, B, C, D is the constant. Constant maknanya perkali kepada nilai. Okay. Kalau A maknanya constant to I1. B constant kepada I2. Okay, tengok A constant I1 ni adalah 1. Constant I1 1. Tengok constant I1 1. Constant I2 I1 lagi 4. Okay. Ni 4. 4. And finally negative 0. There was no I1 here. So 0. Okay. So you substitute according to this expression. So if you substitute correctly, then you will arrive with answer X, Y, and Z. So X represent the value of I1, Y represent the value of I2, and Z represent I3. Okay, that's almost about it of everything. So thank you very, very much. Okay, hope to see you during tutorial question.